I will have to talk a bit slower and cough in between. I'm still recovering from the traditional winter flu, so I pardon myself for that already now. I'm very happy that so many people are here today to listen and prepare a little bit for the hackathon in 2 weeks. And I thought I'd tell you a little bit about how artificial intelligence is or will hopefully one day be used in aquaculture. And we will center this whole topic a bit around the focus of fish welfare and fish welfare assessment. You now have, from the first presentation, heard a little bit about aquaculture, what's the goal of it, and why we're doing it at all. And if you are on a farm, it does not matter where the farm is, land-based, in the sea, what kind of species they are farming, the focus of the farm is on the daily business. It's a hard business, and those people there are busy to bring everything in, get everything done that they need to be doing that day. If you have any, little room for optimization, there's often a focus on economic viability, so reducing the losses and making more profit from it. And what I think is particularly important in a concept or context as we have it now, they're often quite remote. I have rarely been on a farm where there is high-end fiber internet and the cloud services are always available and can deal with any videos at real time. So these are certain constraints that we have on site. And additionally, in aquaculture, there's a certain key people, and we are a lot of biologists and veterinarians. I say we because I'm one of them. And then you have, on the more technical part, you have a lot of engineers, and very fast you go into the topics of economy. And those are also the focuses that people are good at and want to make progress in. Now, I assume that not few of the students here come from computer science. And if we're now talking about artificial intelligence, the focus in those areas are working and demonstrating what state-of-the-art methodologies can do. And the focus is on technical feasibility, like pushing the boundaries of what we can do with the technology. And not rarely you guys rely on a rather high-tech infrastructure, be it that those are good cameras or be it like unimaginable large digital storage spaces that we need. And we have a different key people. We have data scientists, we have computer specialists, we have programmers, we have engineers, but different ones. And very fast you go into marketing. And if you look at those both sides, we cannot expect that everything goes smoothly in between, that all the fancy prototypes that we have transition smoothly from the right to the left and all the input goes from the left to the right. So I thought I used the topic of fish health and welfare assessment a little bit to show what I mean by that. Where are the obstacles that at the moment hinder a little bit that those two, aquaculture and data scientists and artificial intelligence, work at full speed and at full potential together? And for that, I thought I'd make a small detour about fish health and welfare assessment. It's basically, if you have an animal in your husbandry, you should need to know, or should want to know, how good is it doing? How good is it health? And the question is, how am I doing that? So overall, all this welfare assessment, I always mean an evaluation of the well-being of the fish in aquaculture. The reason why we are doing it is that we have quite, especially in Europe, more and more demands from the consumer that they want to eat. And I use strong quotation marks, a happy fish, not least for their conscience. We do have the producers themselves. They want a healthy fish that lives up to slaughter, because every fish you lose before is a loss, it's an economic loss, it's an ecological burden. We have a society that kind of wants a sustainable food source. We have heard that in the first talk. That's why we are pushing aquaculture, because we think it could be a more economically and social sustainable food source than what we have now. And then you have interest from the governments because they need to basically set rules and regulations, and they want to ensure that they are followed. First one. So how do we do it? The idea, the overall concept is mostly that we measure different parameters that we know are correlated to health or to welfare in a certain way. Those can be prerequisites for being healthy, so things we need to have in order for the fish to be healthy. A proper water temperature would be an example of that. And it can be signs of poor or bad welfare. So signs of injuries are an indication that welfare is low, health is bad. And then from all those different parameters that we measure, we extrapolate on an overall health and welfare state. And the key here is then that you need to constantly do these measurements. You need to document those measurements. So you need some way of store the information. And from this, you can then do like what government is most interested in, monitoring, constant monitoring, surveillance of fish health. And then you also have moments when you see, okay, every time I do this measure, the health will improve or it will go down. And therefore, overall, this is a way to improve husbandry. And this is where I come in. Basically, I have an education in ecology and evolution. I did my master's in fish behavior, and I do have a PhD where I focused on fish welfare assessment. I have now spent 8 years looking in this at the Zurich University of Applied Sciences, which is involved into this hackathon. But since last year, I'm now actually in Norway. I'm at NOFIMA, and I do still the same research. We just have a little bit of a different focus. And my focus is on the assessment of health and welfare and the documentation and automation of it. So what I mean by that, we do have the fish, we have them in our husbandry, and my task is basically to come up with concepts of what to measure. So which parameters, if we know, well, water temperature is important, we know blood cortisol could be an indicator, we know that the education of the fish farmers on site are relevant. And then my task is to connect those dots and say, how do those different parameters interact with each other and overall lead or influence fish health and welfare. And where we want to go is actually, we do not want to have like just constantly more and more monitorings, more and more videos, parameters surveyed, but we also want to move down and analyze this data much better than we are doing now. At the moment, like overall aquaculture is stuck, I want to say, at the descriptive level. And what we need to move by having better surveillance, doing better diagnostic statistics with the data, move towards a more diagnostic and ideally in a predictive analysis state. And then once we are there, we can talk about prescriptive, but one step after the other. In order to work a little bit into that direction, I had different projects, and one of them I show a few results of. So of course, we also work with computer vision. And we developed first algorithms where you have fish segmentation. And then we did color clustering. And here you can see the task of the algorithm was to detect the fish within the image, detect certain parts of it, like all the fins. And then we had detection of redness, which is can be both either indication of bleeding, so wounds where the skin is basically injured, or also inflammation when there's a redness. We then put that a bit further and said we want to have this not only in images, but in underwater videos. And we changed the color clustering a bit. And here you have an algorithm that was detecting the fish within the video, do the segmentation, and then say, okay, that's a fin. And then we had the differentiation between a healthy fin here, and then here a fin that had a white edge. Because the white edges, they were nicely visible in water when they have their fins spread out. And it's an indication of a bacterial infection. And you can see a second infected fin up here. After that, we moved a bit further and said, okay, now in a more simplistic setting with just one camera, is it any chance that we can detect body mass? And we were working with different algorithms. You can see here, it's always about testing and comparing. Those are the results from one algorithm. Those are the results from the other. And then you test and compare. My task in all of this, I am a biologist, so I do not come from data science. I'm then doing the weird stuff in all this. So when my computer vision expert said, we need this kind of data, I said, okay, then we kind of do a mobile and float dead fish in front of the camera at certain distances. So you have exactly the data that you need to train your algorithm. And then we see, does it still hold in an actual video? So this is my part. I do explain what we want to see, what fish farmers pay attention to, what our problems are, and where I think there could be help from computer vision and artificial intelligence. And then I work with the computer data scientists, programmers in getting the data that they need to program the algorithms, and then we test them together and see, is it helpful what we program? And there are certain restraints in that. What fish farmers usually wish to have is that you automate things that are constant, because they're really boring to do, things that are very repetitive, because you do not want to have the personnel to do that, or things that are dangerous. And I would like to show you a few examples of things that fish farmers would like to have automated and taken over by AI. And one would be to augment basically the very simplistic surveillance of water quality that they have now. So this is a screenshot from a water quality company. They do surveil any water quality parameters that you can think of. In this instance, it's actually a water level sensor. And they usually are quite simplistic, which means that you can set alarm values. You can say, well, the water is too high or too low, but that's about it. So we have very valuable information that's not analyzed to its full potential, because the alarm was set down here because that's too little water, but already here you can see something is going wrong. So here can AI come in a little bit, or it's mostly very simplistic models actually, where you just say, we know it can go up, we know it can go down, but if it's going down for so long in a certain direction, delta values are a key point here, you can already set an alarm and notification before there's an actual problem. Sometimes this is quite easy because you can have a digital interface between the actual water quality company and your software. Sometimes it's a bit difficult, and you need basically a camera set in between that can like track the graph as we have here, and then alarm for certain patterns. But this constant surveillance and not having alarms when literally shit has hit the fan, but having a notification 2 hours earlier when you still can intervene and save the fish and prevent damage, that's a key part where fish farmers really wish to have like computer science coming in. Another example is a bit more hands-on, as in there's a lot of robotics happening, especially in the processing of aquaculture. Fish are processed with machines, they are filleted in machines, but those machines can be quite sensitive to the shape of the fish. And if you have like a typical perch and all of a sudden you have something like here, that one can get stuck in the filleting machine. And all of you know how annoyed you already are if there's a paper jam in the printer. You can just imagine how much fun it is if you have a perch jam in the filleting machine several times a day. The issue here is that the detection is not done. The task is not complete with just the detection of the fish, because it's approaching the filleting machine on a conveyor belt quite fast. And then if you detect it, if you still need to prevent it from entering the filler machine. So you need to have some sort of, again, robotics that basically swaps it off the conveyor belt. So that's another task where we say, okay, with computer vision, I think we can actually help here a lot and make processing a more smooth process for the people there. Another example would be the daily little points that can go wrong. So this will be a video. You have the tank, you have the mounting of the feeder, you have the feed up here, and you see a distribution of the food. And what's very important that this disc here is rotating, because that's what spreads the feed. If this disc gets stuck, which happens regularly, the feed will just sit there and get jammed, and the fish do not get feed, and the food does not get distributed. So what we do, once an hour, every time you're going to feed, you have to stand there and just have a little look. Is it moving or not? Because that's a task, even though this is a digital feeder, as in it is controlled via software. When does it turn off? When does it turn on? That part is not in any case, in any sort of surveillance. So you stand there every hour checking it quickly, or you risk having your feeder jammed. Again, that's something that with computer vision potentially could be done very easily, because it knows exactly when the feeder should go on. Quickly check, is it moving? Yes, no. If no, alarm someone. Huge potential for the fish farmer to save hours and hours of people standing there, running there every hour, and of having half days where the fish are not being fed. So adding surveillance to a technical infrastructure that in itself misses certain surveillance point, that will be key. And then we come to the actual behavior of the fish. So these were our rainbow trouts. And what we did is a lot of tracking. So you can follow the individual fish, which also means you can say where in the tank they are. And there's a lot of behavior that you do want to see, or behavior that you do not want to see. For example, every time I know I have a signal from the software that the feeder is on, what I want to see is that those are salmonids, all my fish go up. So I should have a lot more traffic at the top of the picture, to the extent where there's so much overlap I cannot track them properly, and I should have an empty bottom. If this is not the case, then I'm feeding not hungry fish and I'm wasting a lot of money. So this feeding behavior surveillance will also be very important, and that's where fish farmers would hope that they get some help. Now a little bit to the question we had before from Bruno was, why is it not easy? Why is it not just done? Why is it not already there? And one point is that we have a very fast development from data scientists with like early prototypes with a given data set. But then what happens with that early prototype? Because usually these algorithms are very difficult to make robust, that they work in any given environment. They are very difficult to make more versatile and more simplistic. And I want to give you a few examples. This is like a top view image of one of our tanks. It's very easy to differentiate the background from the fish because we did something that's very rare. We have a white bottom. It's already difficult enough because you see we have a lot of reflection from the light, which makes computer vision always a bit more difficult. But even if you figure it out, let's say the task will be to count the fish. That's the same tank, the same view 3 hours later. Sun has set. I still want to have the information, but if you came up with color clustering, then you're done. If you did background subtraction, it might still be working, whatever algorithm you came up with, but a lot of stuff doesn't work. We didn't change anything except sun has set. So that's an example of a good idea of an algorithm that is not robust yet. It's not versatile. We can only use it in a square chicken in a vacuum. And that's why we are stuck. Another example, that's side view. We have seen the picture before, and if you're doing fish tracking, it works quite smoothly. You can even see that they are moving round, so you can start counting fish, but here's the same tank a few minutes later. If you're feeding a little bit more, you very fast have very turbid water, and your visibility is strongly reduced. And then another challenge is if you say, please count my fish here, those are rainbow trouts. They have the tendency to move the whole space. And here you have a picture of the same tank, but with a different fish species. If you do segmentation to count the fish, you're done, because that's a bottom dwelling species. They all sit on top of each other, and you have no chance of differentiating, like finding the boundary, drawing a bounding box from around the fish. So these are the reasons why this transition from from artificial intelligence, data science, and computer programming into, let's call it, the real world of aquaculture is set with hurdles. And 3 key points that I would like to give you on the way when you're programming, when you have any projects, is work with cutting edge methods. All you want, that's all good, but develop them till they are done. Technical readiness level 9 needs to work in a proven operating environments. If you're not there yet, then you are not there yet. So go to 9. Have your hired specialist in computer vision, data science, whatever. They are needed, that they will make the progress, but include out-of-field expertise, like a veterinarian, a biologist, to tell you the first problem in the first place, where are the actual needs, and if your algorithm, in the end, your prototype did actually solve the problem that was at hand. And one that's always also for me a bit difficult, sometimes good is good enough. I know that a lot of software programmers have in their minds like the absolute fantastic possibility and potential that the software one day will be having. But if you keep it indoors until it's there, you will get stuck on the way. Sometimes it's okay to sacrifice a little bit of sophistication and go out now, apply it now, make it instantly usable, even though it's not perfect yet, because you also have to have in mind, you have a whole aquaculture group and people that first need to get used to what you are going to present to them. Those people are hands-on people. They are using their hands every day, and they are not all of them are yet used and very comfortable with AI. Not all of them trust the technology yet, because for good reasons. So start slow, get out, get applied what you have now, and we will get there. Everything else will come later. So that was a bit for me from how do we combine aquaculture and data science. And in this setting of the Happy Fish Challenge, the task of bringing the aquaculture topic in it, the needs will fall to Sala, Ranka, and me. We are a little bit the team from ZHAW and from NOFIMA. And in case it is needed, we did prepare a little bit of the data sets that we are having. I would be interested in having the fish count done. I have side view videos and top view videos. I would say not mix them up, but choose either. And we do have a few data sets that will be interesting for fish diseases. Question I did not get answered. Malformation will be interesting, or like severe emaciation of the fish. So I'm very much looking forward to working with a few of your students and seeing where this is heading. I hope I did, but I'm good in time, so we should have some time for questions, maybe even or later. That was me for now.